All right, let's get these exams passed out. All right, so if you could come grab these, Mohammed, Ricardo. I do not believe the grades are on these. They're only on Canvas. Erica. Sorry. Jeremiah. Rasul. Tatum. Irfan. Heidi. Corey. I think that's Corey. No? Is he? Oh, yeah. Okay. Jace. Did you get my email this morning? Yes. Okay. All right. Johan. Christopher G. Jonathan Salinas. You never replied to me the other day.
I was at work at the same time.
Oh, okay. Okay. Christopher Ochoa.
Here.
Gabriel. Michelle. Octavio. Jacob C. There you are. Jordan. Max. Stephen Gibson. Mr. Cope. Octavio. Mr. Cope. Martin. Gina. Is it Christian? Yeah. Okay.
No.
David? Yeah. All right, am I missing anybody? Those are all the exams I have. So you'll notice I don't put a lot of detail as to what you got wrong. All right, and that's because I want you to figure out what you got wrong. I do have some data for the exam. So these are the grades. The average on the test was a 74.4. The standard deviation was 18.2. And those are pretty standard looking numbers to me. Almost a 75 average. And remember, that's like a mid-C. And remember, C means average. So the average score on the test was average. Does that make sense? Yeah, well, I mean, it should be, right? I mean, you should, given a set of normally distributed data, you should always have an average, right? Right? Now, trust me, I would be happy to give everyone here an A if that's what you earned on it, right? So this is data's standard deviation of 18. It's probably the most common standard deviation that I see throughout my entire career. I think the highest I've ever seen on this is like 24, which is real bad. I don't ever like seeing large numbers. And the smallest I've ever seen is like 11. This just tells you how far apart people are from each other. So everyone's kind of within 18 points of that. Look at the grades. 7 A's, 5 B's, 5 C's, 5 D's. I mean, this is like flat. It's not even like a normal distribution. It's like flat. It's weird. I don't normally see this. I usually see like maybe this, and then sometimes I see standard bell curve, but very rarely do I see that evenly distributed letter grades. The graph above shows the highest through the lowest. So the highest score on the exam was the highest possible grade, which is a 105. And then we have a big chunk of A's, and then here are B's, and then here are C's. And look at that, 3 of the C's are actually B's. I mean, those are close enough, right? And then we have a drop off, and then we have this end down here, all right? So that's passing.
Wasn't it at 106?
What's that?
Wasn't it at 106 points?
Was it? I thought it was 105.
It's 106.
It's 106. I didn't.
problems and then just steps.
Maybe when I was grading, I didn't even count the points again. I just remembered 105.
You said 106.
Was it? I'll count it up, and if that, I'll just add a point to everybody. Yeah, not a big deal.
Anything else, man?
Yeah, no, everything helps. Okay, so let me talk about the exam a little bit. Did you feel like you had enough time? Probably not. That's just never going to happen. I don't think you're ever going to feel like you have enough time on a test in Cal 2. You're always going to feel rushed. So let me just briefly discuss these. Problem number 1 is like a pre-cal problem. Problem number 2 and 3 were both just derivatives using chain rules and formulas. And then number 4 was an identity thing you had to prove, right? Number 5, another derivative. So 6 is where the integration started. And I mean, I saw all sorts of things for number 6. I saw people trying like integration by parts on number 6, which, you know, that just to me was like, that's a major disconnect if you're trying to use integration by parts, or even like use substitution. I mean, that's just power rule. And then here's the thing I want to point out. Number 7 is very much like homework problem number 6 in section 5.5. The only difference is in number 6 in the homework, it was 1 over x inside that secant squared, and the denominator was x squared. The approach to that problem was exactly the same as the homework problem. Number 8 was actually number 51 from 5.5, directly out of the book, no modifications, the exact same problem. Number 51 in section 5.5. I'm not saying that was a homework problem. I'm just saying the problem came directly from the book, out of a section that you were asked to do homework in. Number 9 was exactly number 34 in section 5.5. Again, if you had tried these problems, then you probably recognized it. A lot of people did number 9. Well, number 9 was done all sorts of different ways, but number 10, I did a problem like that in class. Number 10. Number 11 was exactly number 20 out of section 6.1. Exactly the problem. Number 12 was number 23 from 6.1. And number 13 was very much like number 8 in 6.1. I think the only difference is that they used sine instead of cosine. So what am I saying? I've been saying do your homework from the beginning. I've also said study your homework, right? Okay? So what I'm saying, and this is tough love, okay? This is tough love. There's no reason to do this on a test where a major majority of your problems came directly from the book, okay? You have to be able to see the problem and know what to do with it. If you're sitting there trying to do integration by parts on a problem that's substitution, when that problem came directly from the book, you're not doing enough. You're not doing enough. You should be doing the homework. You should be practicing other problems within the section, trying to get as much exposure as you possibly can. All right? I'm not saying people are going to fail tests. I mean, I'm just saying when the problems are coming directly from the book, that is a gift to you. Does that make sense? I mean, I think it is. I never got a test where the problems were sitting there, that I could have done that problem if I just tried it, you know? So I'm not saying every test from here on out that's going to happen, but when I tell you to study your homework, do your homework, review it, that's what I'm getting at. I'm not trying to stray away and give you these problems that are, like I go find these harder problems out of different books. I'm staying within the level of the book, but you have to make the effort to do the problems. All right. Should you be worried if you didn't pass this test? I mean, you shouldn't be happy, but at the same time, it's one test, and there's plenty of time to recover. All right, plenty of time to recover. On the other side, if you're in this group, you know, no taking your foot off the pedal here. You have to continue because the material gets harder and more challenging, right? So what now? What do we do? Move on, right? Any comments or questions or anything about the test?
Not about the test, but are we continuing with like examples from integration by parts?
I'm going to start class with one example from integration by parts. Was there something specific that you were?
Oh, it's just because the schedule said we were only doing integration by parts today.
Yeah, well, I'm going to do some more problems that you didn't get tested on.
Sure.
And maybe like one or two, and then we'll proceed. I know it was tough. This test was tough because we talked about integration by parts on Thursday, right? And then you were tested on, wait, am I?
Wednesday.
Right? No, sorry.
Wednesday.
It's Wednesday. So we talked about integration by parts on Wednesday, and then you were tested on it on Monday. I don't foresee that that's going to happen again, all right? And I've had students get upset with me about things like that, but I'm one of the few instructors in the department that does Cal 2 this way. Most instructors will give you one exam at the beginning that covers all the techniques of integration. So we only had U substitution and integration by parts on this test. So you really only had two things to possibly do, right, for these integrals. So even though the test was very quick, it came real fast, at least you didn't have the 5 different methods that these problems could have been. Does that make sense? Less to choose from, faster, as opposed to everything. So that's kind of my take on it. I'm encouraged. I mean, this is good. We got a lot of students that are still doing just fine, and even the ones that I'm concerned about a little bit, you're not like completely out of the game. So. All right, we move on. So I was gonna start class with this problem and see how we do. What I would do at this point is go back through the test, make sure you can do every problem there, right? And if you're still having trouble with it, get with me, talk to your classmates. I'm not doing corrections for bonus points or anything like that. Just you should do your own corrections and just get with me if you have any issues, all right? So I did not tell you all why I was out, did I? No? Okay, so we had a family trip planned for later on in October. It wasn't going to interfere with school at all. And then my wife, those of you who had me last semester know my wife's had some medical issues. She's going to have a surgery tomorrow. So our plans for October got messed up, so we basically had to do our little thing this past weekend, so that's why I wasn't here. With that said, her surgery's tomorrow. We have to be at the hospital at like 4 a.m. So tomorrow I don't think I'm going to be here for office hours in the morning. And then Friday I won't be here also because she'll be recovering and stuff, and I'll be with her. So I'm hoping that if everything works out fine, that I will be here for every test from here on out, all right? So this won't happen again where you have a proctor. Corey, where's Corey? All right, Corey. Did you get your test? Yes? Okay. Corey, welcome back. Any ideas here? I'm expecting that this is going to be not good. Yep. Everyone understands it's not just sine of the square root of x, right? Okay. So it's not something we know. Basic U sub. Choose something, the derivative. So what would be one thing you could choose for U sub? Like if you were trying to, you could do cosine of the whole thing, right? But then the derivative of that's not here. You could do just the root x, but the derivative of the square root of x is not here, right? So it doesn't look like U sub. And then the other thing is integration by parts. What's the issue, Corey, with integration by parts? If we were to set up our table, we have to choose a u and we have to choose a dv, right? So what would be maybe a choice for u? Okay, but remember, square root of x is inside the cosine, right? So you can't grab just the square root of x. You'd have to grab the whole thing, wouldn't you? Because that's not multiplication. So really, if you did that, what's your only choice for u? Cosine of root x. I mean, that would be your only choice. And then dv has to be dx. That's your only choice. And what's wrong with this? Nothing's wrong with it? V is x. Okay, that wouldn't be bad. What about du? What's du?
It'd be x sine square root of x over 2 squared.
Yeah, negative. Let me do it this way.
Oh, yeah.
Right? Sorry, dx. So you would have to use chain rule. Derivative of cosine of something is negative sine of it, and then times the derivative of what's in there. So you get this, then times this. So your new integral is going to be voodoo, right? These two, and that doesn't look very nice, does it? Because now you got sine of root x, and you got x and then root x all together. So that doesn't look that great, right? So maybe, I believe this is kind of an open question. I don't know, maybe that does work. That's all I'm going to ask of Corey for now. Jeremiah? Do you agree, Jeremiah, this is no good so far? Like it doesn't look like anything's going to work? Or do you have some idea of trying something different? You think that one over there will go? Okay, well, let's take a look at it. All right, let's see. Let's see why I'm avoiding this. If we stick with this, this becomes ultraviolet minus integral voodoo, right? Okay, so ultraviolet would be x cosine root x minus integral. Okay, so this and this together, I have a 1/2 I can pull out. It's negative, right? So it becomes plus out here, plus 1/2. Okay, so what's still in here then, Jeremiah?
Square root x, sine, square root x.
Yeah, square root of x, sine, square root of x, dx, yeah? So you got the square root of x here by doing that x and dividing by root x, right? And that gives you square root of x. So this is our new integral. This integral right here is still pretty bad. Yeah?
Can I take cosine to the cosine x to 12 half?
You could rewrite this as cosine of x to the half, like that. But you cannot write it as cosine x to the half. That would not be right, because the square root is only on the x. Is that your question? Mm-hmm. Yeah. Yes?
Can we do just square root x for you?
For where? For you?
For you?
For here?
Square root x?
Right here? In integration by parts? You cannot, because this is not, it's not cos times this, right? It's cos of this. So you can't, now you could use square root of x if you were doing basic u substitution. Yes?
I had a question about that, actually. So like when we did the voodoo part,
Mm-hmm.
it's square root of x sine square root of x over square root of x, right?
Square root of x sine, no, it's x sine square root of x.
Oh. So where did the square root of x come from then?
That's a terrible square root. Right here. That's square root of x. Right? X to the 1 over x to the half is x to the half.
Oh, I see.
Subtract the
I see
exponents.
what you did there.
Right, Jeremiah? That's what you had done that, right? I guess.
Oh,
Yeah. So? Just show you?
We tried like 6 different ways.
Well, we never tried a basic u substitution. Jeremiah said it, but he didn't mean it. But it's okay. We're still going to do it. He said let u be root x, but not with integration by parts, with the basic u substitution. And this goes against everything that we talked about really with u substitution, which is you want to pick something and its derivative, you want to see its derivative there, not trapped, right? Okay, so if we pick this right here, that's going to be u, right, in here? The derivative of that doesn't appear here anywhere. right? So this seems very unnatural to choose this, right? But it's going to work. And so if it's going to work, that should be somewhat demoralizing, because now you realize that this method might work for problems even when it doesn't look like it's going to work, right? Yes?
So for it to work, would you have to say that you have to have the vision to see that when you take the derivative of that through chain rule, then what we're looking for appears?
Quite honestly, I know this is going to work because I know it's going to work, but I don't even see why it's going to work yet. So you won't be able to necessarily see why it's going to work until you do it. So if you're looking for something as like what would tip you off to do this, it's that whole mentality of, well, you better try something, right? It's that sort of, let me just take a swing and see what happens, right? So let's go ahead and take the derivative of this. Du would be 1 over 2 root x dx, right? Which I don't see over there, right? I don't see that over there. The only thing I do have is I have, dx is over there, right? So I've never done this before. I've always told you, like, don't mix the u's and the x's up, right? But I'm going to isolate this. So I'm going to multiply both sides by 2 root x. Right? I've like specifically told you, try and avoid having x's and u's mixed, right? But do you see what this can become? 2u, right? Because what's the square root of x? It's u, right? So now I can rewrite this as 2u du equals dx. Yes?
You can also just, like, you can square, like, the very top of it,
Uh-huh.
you can square the u right, and then you can u squared equals x, and then take the derivative implicitly. And then
Oh, in the very beginning, yes. So if you wanted to, in the very beginning, you could go u squared equals x, right? That's legit. And then take the derivative of this, 2u du equals dx. So you take derivative on the left and right-hand sides. This expression is equivalent to this expression. So yeah, you could do either way. I'm just doing it this way because this is the way we've kind of done it. And so at this point, like algebraically, we move this over here and go, whoa, check that out, okay? So now let's rewrite the problem. Maybe we'll be able to do it. This integral becomes cosine of what? U. And then what's dx? 2u du. Now, be real careful here. These two u's cannot go together, right? This u is inside this cosine. That u is not. Right? So now I'm going to rewrite that as 2 integral u cosine u du. Now, did our lives get any better? Yes, it did. Because this we can do using what? Integration by parts. Right? This is basically like, this is like the integral x cosine x dx. That's basically what it is, right? And so what you say is integration by parts. If I choose this to be my u, in the new integral it's going to go away, right? And then if this is my dv, then in my new integral that becomes sine x, and so I should be able to do that, right? So this is a very unnatural substitution that leads you to an expression, an integral that you can do with integration by parts. Yes?
When you use u for u,
When I use u for u?
on the integration.
Oh, on integration by part. I'm not going to use u for u.
Oh, you're not.
I'm going to use a different letter.
You are.
Yes. Yeah. Because I don't want to have u mean two different
But
things.
then you'd have two du's and one.
Exactly. So what I'm going to do now is integration by parts on this. And I'm going to do, well, I can't use u, so I'll use w. W equals u, and dv, I can still use dv, will be cosine u du. So the whole ultraviolet minus voodoo is now gone, right? Because we don't have u and v. So it's like ultraviolet. It doesn't make any sense anymore, right? That's why I like the table, because I always just work off the table. My new integral is going to be this times this minus the integral of this times this, regardless of what the letters are. Okay, so what goes here? dw equals du, okay, and then what goes up here? Sine u. And so now this, let's move this up here. this becomes 2. All right, 2, and now we're using the formula. So ultraviolet is really this times this, which is u sine u minus integral. Okay, what's my new integral? Sine u du. And on that, antiderivative of sine is negative cosine. So that we can handle, right? So now we've got equals 2 bracket, let's see, u sine u. This should turn out to be plus cosine u. And then plus c. I don't know if I addressed this with everybody, but a student did ask me a while back about this plus c, whether or not that plus c needs to be here with the 2, like inside here, or outside. And the whole idea is even if you did plus c in here, and then distributed a 2, you'd have 2c, right? But 2c is still just a constant, right? It's just some constant that we don't know. So it doesn't matter if you call it c or 2c or pi c. It's just a constant. So we can just tack it on to the very end. All right, we're not done, right? What do we need to do now? Distribute the 2 and replace u with square root of x. So this should become 2 root x sine root x plus 2 cosine root x plus c. There we go. That's the antiderivative of cosine root x.
That's a real son of a gun.
Yep.
Dang.
That one is an unnatural sort of substitution there, huh?
All kinds of witchcraft.
Mm-hmm. Okay, on the next one, I'm just gonna, I think we'll get it set up to the point where we know what to do with it, and then we'll proceed. We'll stop at that point. So how about, while you're looking at that, I'm going to put here versus so the problem I want us to do is on the left, but I want you to look at the problem on the right and compare the two. So how would you do the problem on the right? Integration by parts. What would you choose for your u? T cubed. And then the dv is this piece, right? And when you integrate that, it should be pretty straightforward integration on this. Just a few times, and you'll have to kill off, t cubed becomes t squared, then t squared becomes t, and then t eventually goes away. So this one's doable, yes? Why is this one not doable the same way?
You're going to have one half. You're going to build up a bunch of one halves.
This right here we can still use as u, right? And make it go down power-wise, but you have to integrate this. And the antiderivative of e to the negative t squared is not easy to do. In fact, it's not possible. All right, so here we could integrate e to the negative t. We can do that because it was t, not t squared. But this integral, if you had to do it, is not happening. There is no method for that, so we'd be stuck. Understand? So integration by parts does not appear to be good for this, yes? So what then? What did we just do in the last problem? Made a substitution, right? Even though it didn't look like it was going to work.
If you break apart that t cubed to t times t squared and use that, you use the negative t squared as your u.
Like this. Rewrite t cubed as this, and then use your u as what?
As the negative t squared, the exponent,
Okay, so the derivative of that would be
just 2, or
negative 2t, which you kind of have, and then this would, in some way, would probably be related to u?
probably
Yes.
solve for it.
Yeah, okay, let's try that. So this would be u is, you want me to go with the whole thing, negative t squared, or you want me to go with just t squared? It's up to you.
I mean, if t squared works, it's probably easier.
Let's go t squared then. Let's go with t squared. Basic substitution here.
Don't you want it to be negative?
We talked about, it could go either way.
okay.
It's just without the negative, it would just be easier derivatives, don't have to keep track of it. So now this becomes, let's see, du is 2t dt. And do we have that? We don't. We have a t dt, right? T dt right there. Yeah, see, so this t squared is going to be replaced with u, right? And that t squared will be replaced with u.
So we could do 1/2 du.
Yeah.
t dt.
1/2 du equals t dt. And now we should be able to rewrite it all. Heidi, what's the new integral? What's our new integral? Okay, so 1/2, I'm going to pull that out. 1/2 du, that's the purple stuff, right? Okay, and then this is u, e to the negative u, right? U e to the negative u. Now, can we do that? That we can do with integration by parts, because we no longer have that thing squared anymore, right? So if you do integration by parts on this, you would, well, we can't use u, right? So you would do maybe like w again. W would be u. What would dv be? E to the negative u du. This to here would be dw is du. And then moving up, this would, what would that be? Negative e to the negative u, right? So what's in your new integral? What would be in the new integral? This thing, right? And that's doable because there's just du here and this right here, and you can integrate that. Yeah? So we would be okay at this point, I think? Take it the rest of the way? Okay. Okay, now we are putting integration by parts behind us. And we're going to move on to the next section. What? What? Whoa. Oh, there we go. So 6.2 is broken up into two sections. Oh, wait. Hold on. Where is it? That's right. Hold on. Where is it? 6.2. Uh-oh. There we go. 6.2 is broken up into two sections. The whole section is called Trigonometric Integrals and Substitutions. So what we're going to be doing most of today is what we call trigonometric integrals. That is, integrals that involve trig functions and just trig functions. And then later on, we will learn, or next class, we will learn how we can do this new substitution technique and employ what we know about this stuff to do problems. So 2 separate ideas. They are connected, but I want you to look at them as separate for now. And we have to get some preliminary stuff kind of out of the way. So things we already know. Obviously, the antiderivative of sine is negative cosine. Antiderivative of cosine is sine. We know that if we have sine of ax, so like sine of 4x, that if you want to take the antiderivative, you have to do negative 1 over 4 cosine of ax. So that would kind of scale out. We did talk about that, right? And same thing for cosine. We can scale, we'd have to scale out if there was some linear expression in there. So now we get to trying to find antiderivatives of integrals that involve various powers of sine and cosine. So let me get to an example first. Take a look at this one right here. Sine cubed of 4t dt. That is an integral that involves a power of sine, right? Look at the next one. Sine squared x cosine to the 5th x dx. That involves various powers of sine and cosine, right? Mixed. And then look at this last one. Cosine to the 4th beta t dt. So all 3 of these integrals involve various powers of sine and cosine. Agreed? Okay, so how do we attack these? Well, I wrote it all out here. These are little like strategies and what you can do to attack them. And if you like to memorize strategies, you can. What I want you to really remember is that we are going to try and use the Pythagorean identity. Okay, so let's make sure we remember the Pythagorean identities. I'll put them over here. What is our Pythagorean identity? Sine squared x plus cosine squared x equals 1. Another way I could write that identity is that sine squared x is equal to 1 minus cosine squared x. Another way I could write that identity is cosine squared x equals 1 minus sine squared x. Yeah, right? That's 3 different versions of the same equation, right? So let's just go right to a problem and see how we are going to attack this. I'm going to write this down over here. And then sine cubed 4t dt. And I'm going to try and do this without going through and giving you like a process or a set of steps. So I see sine cubed, right? I see sine cubed. Now, if you start going through your little Rolodex of things, there's no basic U substitution. Integration by parts is not going to work either. How do you know that? Well, you'd have to kind of try, and then you'd realize it's not going to. But then you see it's sine to a power, so you start thinking, oh, we went through this 6.2, which had to do with sine and cosine raised to power. So, what did he do in class? Well, I see sine raised to the 3rd power. So what I know is that I can rewrite this as sine squared 4t times sine 4t dt, right? I mean, that's just because it was cubed. I could always peel one sine off, and I'd be left with sine squared and then a sine, yes? If this was sine to the 5th, I could peel one off and I would have sine to the 4th, right? Sine to the 7th, I could peel off one sine, I'd have sine to the 6th. Now, why is that useful? Well, we know that by itself, right, that's the derivative of cosine, yes? I mean, without the negative, who cares? But that, if there were cosines over here, then that would be the derivative of it, yes? Now, can you rewrite this in terms of cosine? Yes, because you have a Pythagorean identity, right? Anywhere you see a sine squared, you can replace it with 1 minus cosine squared. What if this was sine to the 4th? That'd be sine squared squared, right? And so you could rewrite that with cosines and then square it. You'll see, I'll do one. So anytime that's odd, if we peel one off, this should be assigned to an even power, and then we need to use Pythagorean identity. Yeah? So now let's just go to the Pythagorean. So that is replaced with what? 1 minus cosine squared what? 4t. Right? And then what do I still have here? Sine 4t dt. And now at this point, Russell, basic U sub. What's U? Do you see something in its derivative?
4t.
4t, go for more. Remember, we peeled this sign off, right?
Sine 4t.
Okay, so sine of 4t, if that's u, what's its derivative? Cosine 4t. Do you see cosine 4t?
Yeah.
Where is it, though? It's trapped in a parenthesis and being squared. You don't want that. You never want the derivative to be trapped somewhere. So can you do it the other way around? What about letting u be cosine 4t, right? Then its derivative is over there. We're off by a little bit, but it's over there. Do you see that? Okay, so let's try this basic u sub. If u is equal to cosine 4t, the derivative of that is negative 4 sine 4t dt. Do we have that? Do we have negative 4 sine 4t dt? Kind of, right? We have that, don't we? So I can just multiply this negative 1/4 du on both sides? Negative 1/4 on both sides? Chris Ochoa. Are you following me so far? Okay. I'll give you a chance to jot anything down if you want. I'm ready to rewrite the integral in terms of u.
Okay. So move the 1/4 to the front.
Okay, negative 1/4 out front, integral.
And then 1 minus
1 minus.
cosine squared u.
Okay, what is the cosine 4t
It's
being
u.
replaced with? U, right?
Yeah.
But it's still squared, right?
So u squared.
U squared. And then,
this, yeah, d
yep,
du.
du.
Yeah.
That's it, du.
Pretty cool.
Yeah. Now, how do we do this? Power rule. This is straightforward. Look, we have this subtracted from this, right? We just do these individually. We can take the antiderivative 1, antiderivative of u squared. So this is going to become negative 1/4. I'll use a bracket here. Antiderivative of 1 is what? U, because my variable is u. So u minus antiderivative of u squared. 1/3, u to the third. All of that plus some constant, right? Last step. Replace u with cosine 4t. So the antiderivative of this should be negative 1/4 u. U is cosine 4t. And then I'm going to distribute that through. So that's going to be plus 1/12. And then u, which is cosine of 4t, but raised to what power? The third. So I'm going to put cubed right there. Plus c. There it is. What do you think? Yeah. So I think in theory that should work for sine to any odd power, right? Yes.
Is it wrong if I put my cube on the
On the what?
by the 14?
It depends on how you write it. If you write this, that's wrong, because that's implying that you're cubing that. If you write it like this, then you're good. So this and that mean the same thing. Which is why we write it here. Like, it's kind of weird that that's there, right? But the reason we write it there is so that you don't write it this way and there's confusion as to what you mean. All right, so let me change the problem. Let me change the problem, just so we can appreciate this, how this could work. What if this was sine to the 7th 4t? Then how would that change things? Could I still peel off a sine like I did before? Yes, but now this would become sine to what? The 6th. The Pythagorean identity does not, like, I hope you all understand that the Pythagorean identity does not extend. In other words, you can't just like say, oh, if it's squared there, then it becomes 6 there, 6 there. It does not work that way. But we still do have it, right? So now I can rewrite sine to the 6th as sine squared 4t, right? Raised to what power?
3.
The 3rd power. Now I'm using brackets, you could use parentheses. Right? Sine squared, that quantity cubed. And then the next line I could write, okay, 1 minus cosine squared 4t, that quantity cubed sine 4t dt. Make sense? Now do your u substitution. U is equal to cosine 4t. Same du. I'll go ahead and kill off a step here. So I already knew I was going to get a -4 here, and I divided it through. Okay, so that's the same thing as what we did before, right? So now, Martin, what would my new integral become in terms of u?
It'd be 1 minus u, all that whole quantity cubed.
So 1 minus u squared, right? So that's 1 minus u squared, but that whole quantity now cubed, and then du, right? And then we still have the -1/4 out. So this doesn't work as easy as the last one, right? The last one we could just do each one. But what could we do? It's not fun, but what could we do? We could just expand it, right? I mean, it's a little bit of work, but we could just expand, right? 1 minus u squared times 1 minus u squared times 1 minus u squared, right? Like what would we get if we did 1 minus u squared times 1 minus u squared times 1 minus u squared? Do you agree we're just going to get a polynomial?
Yeah.
And so we'll have a bunch of terms, and we can just integrate those term by term. So I'm going to say at this point, dot, 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 like check. We could do this. Not fun, but we could do it. Now, what you wouldn't want me to do is like make that sine to the 77th power, right? Then you still peel off a sine, then you got sine to the 76th. And then you have a huge expansion, right? Which is why we have formulas, these power-reducing formulas. I started showing it to you at the end of last class, but we stopped. All right, good or no? Yes?
I just have a question about the substitution one.
Yep.
When we're using cosine and 4t, I know
Yep.
in past problems you'll grab like the constant, you'll grab 1 minus cosine.
Because, okay, so why didn't I grab the whole thing? 1 minus, because I would have had to have grabbed 1 minus cosine squared 4t. And then when you take the derivative of this, you've got chain rule on this. You get 2 comes out, cosine. See, you're going to have, this is too much. Now, I agree with you. If that squared wasn't there, I would have grabbed the 1 minus also. Good. I'm glad you mentioned that. All right. Shall we try something a little different? Okay. How about, well, would things change dramatically if we did something like cosine to the 5th of pi x dx? We have cosine to an odd power, right? Cosine to an odd power. So could we peel a cosine off? We could. So this becomes cosine to the 4th pi x times cosine pi x dx. This time, the cosine pi x is the derivative of what? Like this piece right here is the derivative of sine of pi x, right? We're off a little bit, but so that means I need to somehow switch those into sines. But I can use the Pythagorean identity again.
Yeah.
This time solving, for cosine instead of sine squared, cosine squared instead of sine squared. But first I'm going to rewrite this as cosine squared pi x squared. Do y'all see that this is the exact same thing we just did, but we're doing it with cosine instead of sine? Okay. So cosine squared pi x becomes, Mohammed?
Yes.
Cosine squared pi x becomes,
1 minus sine pi x all
yep,
squared.
1 minus sine pi x. And that's squared here, right? It's 1 minus sine squared pi x, but then all of that squared cosine pi x dx. So what's my u going to be here then?
Sine squared by x?
Sine, not the squared, just the sine pi x. Okay, so u would be equal to the sine pi x. Derivative of that. What is a derivative of that, everyone?
1 over pi cosine pi.
That's antiderivative. Be careful. We're taking derivative. Right? So the pi is just going to pop out.
Yeah, it's 1 over pi cosine.
Oh, wrong way. Derivative, not anti.
Oh, my bad. Pi.
Pi. So we get pi cosine pi x, right? Dx.
I was thinking 1 over pi du.
Oh, yeah, okay, got you. Yeah, so that's going to be my next step. We have cosine pi x dx here. There's cosine pi x dx there. So I'm going to, multiply both sides by 1 over pi or divide by pi. Okay, there we go. We should be able to rewrite this now. So this becomes, let's see if we can get through everyone today here. Let's see. Max is up. Okay, what's our integral in terms of u?
1 minus u squared all squared.
1 minus u squared all squared. Good.
And then times du.
du.
It's going to be a 1 over pi in the front.
Yeah, we'll just throw that 1 over pi out front. Remember, pi is just a number, so it may as well be like a 4. We can just pull 1 over pi out. And Max, you could handle that? You think? How would you do that, Max? Expand it out, right? So just square that thing. Let's actually square that, because squaring is actually a little easier than cubing like the last problem, right? So if I, or no, it was, wait a minute. Did we have cubed on the last one?
Yeah. It
Was
was
it?
7.
It was, oh yeah, it was the 7th, that's right. So here we just expand it. So that should be 1 minus 2u squared plus u to the 4th, if we expand that. And then that du. And now these are pretty straightforward. Antiderivative of that is u minus 2/3 u cubed plus 1/5 u to the 5th plus c. So do you remember me talking about, when we first started doing antiderivatives, how everything builds on itself, right? So in this problem, we used u substitution, right? And we used power rule, right? So we've used two. We didn't use integration by parts, but you can imagine maybe there might be a problem down the road where you have to do integration by parts and use substitution and power rule, like all in the same problem. And yeah, could happen. Will happen. Will happen. I promise it. Guarantee it. All right. So if you understand the last two kind of formats of what we've been doing, then what could we do as a problem to start out that might kind of cause us an issue then? Like I've intentionally made this a certain way.
He has like a square root of quantity.
The square root, that's more painful than I want to discuss at this point. But baby steps, right? Yeah. So like make it an even power to start. Right? So let's do that. Let's change this problem. Let's do a new one. Would we be in trouble if we make it an even power? So let's go with something clean and easy to start. Cosine squared x dx. That's pretty clean, right? Now, could you still peel a cosine off? Yes, but what's wrong with that?
He wouldn't match with
what was left, that cosine that's still there, you can't use a Pythagorean identity on, right?
Can we not?
Now, I could use Pythagorean identity right now, couldn't I? But what would this become? 1 minus sine squared. And does that help you? So even if you don't write this down, but let's say you rewrote this, you're like, haha, got the Pythagorean identity, right? Haha. Okay, now you could find the antiderivative of this, right? Sure? Okay, but how do you do that? See, you're still stuck with the sine squared. You still don't have a way, right? U sub, if you use U sub, you need the derivative of it there somewhere. So let's say here you let U be sine x. The derivative is cosine x and it's nowhere to be seen. Here, if you said, let's let U be cosine x, the derivative of that's negative sine x and it's nowhere to be seen. So do you see how important it was that it was an odd power earlier? We could peel one off and that became the derivative of something. You see the problem, the issue? So when we have this situation, our Pythagorean identities are actually not going to be the identities that help us. It's a different one. So the identity that we're going to use, it's referred to differently depending on your textbook or the way you learned it. I won't bring it up in the notes. I'll put it up here and then I'll write it down over there. These are what I call the power reducing formulas. So there was a formula that said that if you ever had sine squared x, that became 1 minus cosine 2x over 2. Does that look familiar? Pre-cal. This is also the same as 1/2 times 1 minus cosine 2x. So this formula says if you ever have sine being squared, right, that if you'd like to reduce the power and no longer have a squared trig function, you're free to use this formula. You're going to wind up with a cosine, but it's not going to be squared anymore. But the sacrifice is now you've doubled your angle. So whatever your angle was here, it now gets doubled in the formula. So it's a give and a take. You kill the power, you double the angle. All right, so that's the formula. You need to know that one. And then the other one is the one for cosine squared x, the way to reduce that one down. And the formula is very similar to this one. The only difference is a plus between the two. And both of them have cosines here, cosine 2x. And then here we could factor the 1/2 out. Okay, so I'm going to write them over here. So these are our Pythagorean identities. Here are our power reducing formulas. Sine squared x equals the one that I'm going to use is that one. And cosine squared x equals 1/2. Now, I don't recall if these formulas are on your formula sheets. They are? What reference page is that? Reference page 2. Yep. So bottom right-hand corner, they call them the half-angle formulas. And I've never liked that name. Because to me, this is a formula that reduces your power, right? It does reduce the power from a squared down. The only way I see half angle from this is that that angle is half of this angle. But it actually comes from the half angle formula and you solve for this. So it's related. But I like power reducing because we want to reduce the power. That's what we are trying for. All right, so you have these formulas available to you. You ready to use it? So here we go. We've got a sine squared, or a cosine squared. We're going to start out. Because this is an even power, we know we're not going to use a Pythagorean. Instead, we are going to power reduce. So that, I'm going to go straight to this formula right here. It becomes 1/2, parenthesis 1 plus cosine 2x dx. And that is actually, yes? Oh yeah, I'm going to. Okay. Yeah, I put the formula right there. Yeah, so let's just yank that half out. And then 1 plus cosine 2x dx.